Okay, we are recording right now. Okay, so we were here and we were trying to understand how an MLP takes inputs probably which are not linearly separable and then warps the space in the hidden layers where there is nonlinear transformation, so that at some level there is linear separation, and thus you start solving problems which are a bit more complex, which have complicated boundaries, and those are the types of problems that we pretty much encounter in the real world scenarios. Okay, so let's talk about a generalization of the feed forward neural network, right? Like we saw two layers, there can be many layers, n layers, right? So we have input units, we have say a couple of hidden layers and many output units depending upon what we are trying to predict. The output units could be anything here. It could correspond to a specific type of a prediction about the input state, like if this is input is an image, right? Then the output could be whether it is the image of a cat or the image of a dog or something like that. Right? So output can predict what the input image presented is. So this is a very straightforward network with all-to-all connections. And in fact, when we go in the neural network this way, that is from the input to the output, it is often called, let me erase this. It's often what's called a forward pass. Okay, the forward pass. All right. So forward pass is nothing but what you are doing is at every stage, you are combining your inputs with some weights and summing them up. And that's some node here, right? And then you are passing it through a nonlinearity or a nonlinear function or a nonlinear activation function, f, right? And at that stage, the input to the next layer is yj in this case, right? Which is um, the sort of the nonlinear transformed output from the first initial input stage that forms the input to the next layer, and where zk now, which is the input that goes into hidden layer number 2, right? So which is wjk into yj, which is the output of the first layer, and so on and so forth, right? So that's nothing but the forward pass. So basically at each stage you are taking the weighted sum of inputs and passing it through a nonlinear function. Okay, and it happens so that the way this network is arranged tells you a lot about the properties of the network, right? Like when it is a feed forward all-to-all connected network, that has certain properties of solving certain problems. But if you change the architecture, then it looks like you can start solving some different problems as well, right? For example, you know that you must have seen CNNs or RNNs. They do not have a similar structure, but I'll show you how similar principles apply to those cases as well. Okay, that is, you have a forward pass where you are trying to combine inputs through weights and get to the next layer, and so on and so forth. And then there is a way to do what's also called a backward pass. We'll look at it. Okay. Now, before we even go into any of the functioning of the neural networks, we need to understand what are errors and loss functions. Anybody can tell me what are errors, loss functions? What do they actually mean? Any
Like
idea?
definitely it is doing some operation in different nodes, so
Mm-hmm.
some errors will be generated which can be handled
Mm-hmm. So,
extensively.
yeah, yeah. As in, uh, there's some objective of the neural network, right? What is the objective typically? What do you want to do? Or
To
what?
predict.
So predict something, right? You want to predict something, and typically when the network initially is what's called untrained, the predictions will be bad, right?
Yes.
Yeah. So in some way, we need to say how far the network is away from what we actually want it to do, right? And in order to do that, we need some measure of an error or a loss. right? In some sense, we need to tell the network, oh, you are this far away from what you want to do, and how can I exactly do that, right?
This means like difference between both, right?
Right.
What you are predicting and what you will predict by network.
Absolutely, right? So since these are in some ways supervised networks, right? So we know what our target is, or we have information about the targets, right? This is what we want. And we have what is coming through the network, right? So the network generates its outputs. And in some sense, you are sort of comparing between these two, right? And seeing how far the network is away from what sort of target you want it to achieve. Okay. So in order to do that, you need to understand two things, right? Where do you actually estimate the error, or where does the error actually make sense, right? In this hierarchy, where do you think an error or a loss function should be computed?
Output layer.
At
So
output layer.
why the
Output.
output?
Output
Because
means-
we'll get the prediction, and then we'll, based on that actual value and the predicted value, we'll take a subtraction and then
Right. In some sense, that we need the output to be an interpretable quantity, right? Or at least at some level where you tap out of the network, at that level, you want the network to produce something meaningful, right? Right. For example, here you want it to predict some, pattern or trend, or identify an image or whatever it is. Right? Now we need this. Therefore, we need this layer to be the layer that's high interpretable, and so that the output layer, or what is coming out of this network, right, that's where you need to compute your errors. So in that sense, what we have is a model prediction, right? That is y hat. I call it y hat because it's not close to the true prediction yet, and you have your target output y, right? Fine. So this can be anything. This can be numerical, categorical, and so on. And then we look at some of the examples. But there's something that the model predicts, and then there's something that's your target. So let's take an example of, say, sets of y hat and y. Let's say a neural network with inputs x1. When I say x1, you can think of it as a vector, right? So x1 is probably a three-dimensional vector, right? If there's a question, people can just shout it out.
Sir,
Mhm. Sorry, I can't hear you.
yeah, I can hear.
What is it? Do you want to ask some question? Sudarshan, we can't hear you. So if there's a question, then please speak up. Otherwise, please mute your mics. Okay. Thank you. So to continue, x1 is let's say in this case a three-dimensional vector, because you have a three inputs that's coming into this network, right? And let's say at the output, the predicted output for one of the nodes, say for this node, right? This, so yi.
Sir, sorry to interrupt. A couple of them are waiting in the lobby to join the class.
Okay, just a second. Please join with your IITJ ID. If not, because if I have not added you to the class, I don't want to add external people into it, and that's why I'm, let's see who's in the queue. Okay, so these two are IITJ IDs. Okay. Yeah. So I think I added them. So if you want to be added to the class, let me know. Okay. Please send me an email, because then it becomes very disruptive in the middle. All right. So as I was mentioning, for a given input x1, we have a model prediction that's y hat, say of I, right? So let's say that's this case, right? Like we have 4 different inputs, x1, x2, x3, x4. And for each input, you see a particular y, right? So in some sense, what you are doing is computing the error between what the model predicted. So in this case, the output is 0.1 and you want it to be 1. And let's say this case, the outputs represent some sort of probability distribution. Right? So that means what is the probability that the given input is the image of a cat, right? Their expected value that you know that's a cat, then that's going to be 1. And the network predicts close to, say, something like 0.1. So there's an error here, right? So y minus y hat is, say, 0.9. Okay. And then in another case, you present another input, and then this is your target, and this is your desired, and you have these errors, right? So there are two things here. One is the error, and one is what's called the binary error. Okay. The error basically tells you the magnitude as well as the scale. That is, how wrong is it? In which direction is the mistake going, right? Is it overestimating it or sort of under predicting it, right? Is it saying something is a cat when it is not, right? That's when it becomes negative. And when is it sort of doing the other way, where it is a cat but it's predicting it's not, right? So those are both scaled as well as signed. So this often is used to train the network. Right? You use these errors to train the network using certain algorithms like backpropagation and so on. But if you see that this binary error is telling you about something about the scale of the error, right? Let's say I take an error difference threshold of, say, mod of y minus y hat greater than 0.5, right? So basically, I'm saying any error that is greater than 0.5 in its magnitude, I want to mark it. Okay. So that means these two get marked, whereas these don't. Right? This can be used to evaluate the network in some sense, that is it doing well, right? Because if the number of ones start reducing, then the error is shrinking. Right? So this can be used to train the network, and this can be used to actually evaluate the network. Okay. And in fact, we will use both of this information in, say, some coding examples that I'll show you, that you look at how this is informing the network how to train, and this is informing how we can evaluate the performance of the network, right? Like how well is it doing? Okay. Any questions here?
So to train a feed-forward neural network, do we always need label data in the sense that we always have
Yeah.
a Y to train it?
Yeah. You need to have at least some form of supervised data which will help you understand what the target is, right? And there are often other networks where you do not typically need label data, like for example autoencoders, right? Have you heard of those, where you don't need any sort of label to the data? You just need the data itself, and you're trying to somehow dimensionally reduce the data and get a compact representation of it. So those are slightly different types of networks. But for a feed-forward network where you have an input-output mapping, you need supervised information, right? You need some sort of target that the network can learn.
So what is basically different between feed forward and feedback mechanism?
We'll look at the feedback. We haven't looked at feedback yet, right? We haven't looked at the backward pass.
General term,
Just,
what is different? In a
sorry?
general term, in a general term.
Okay, in general terms, I see the feed forward idea is that the network goes in one direction only. For example, if there are other types of networks where information from one node can go actually back, right? There is what is called a recurrence. We look at recurrent neural network. So this is where feedback comes. Yeah? This is feedback. Yeah. So that means that as information is going through, it's also coming back. So that's the idea. Whereas here, the information directionality of the information is always in one side, right? One direction.
Got it, sir.
So, yeah. Okay. So if this idea of error is clear, right? Because the idea of loss function is slightly a little bit an additional concept to this, but you see that our aim is to minimize this error. That's basically it, right? You want to somehow bring this closer to what we actually want. Now, let's talk about loss functions, right? One of the very famous loss functions that typically is used in ANNs and deep learning literature is mean squared error, right? Anybody know how mean squared error is formulated?
Yeah, summation of y minus y cap divided by
Yeah,
number of
yeah. So it's typically used for continuous data or numerical predictions, because there is another sum of laws which is used for probabilistic data, but we'll look at that in the next thing. But for continuous data or numerical predictions, we use a loss like this. Okay, loss is often termed by this fancy L, right? You must have seen this in papers and literature. But it's nothing but y minus y hat the whole square. Okay, now, and there is a 1/2 here, but why choose such a formulation of a loss function? Anybody have an idea? Why y
because
minus
we
y hat the whole square?
because we don't want value in minus.
No, I mean, that's usually the answer I often hear. But can anyone think of a geometric interpretation of
Yeah,
why this?
this function is continuous forever,
Okay, okay,
and also it is never discontinuous. It is symmetric.
that's fine. But there is one more property.
The
What sort
line
of
shift.
function is it? What sort of function is this?
It's a convex function.
Fine, but a little bit more basic.
Square function.
Basically, the line shift. Basically, the line shift when we draw a particular line that is best fit for all kind of data points. So it's basically line shift means how far the displacement is from the predicted line of the
That's okay.
actual
That's
data
all
points.
fine. That's all fine.
It's a
But
square function and it can have a minima.
okay. There, someone has come to the right thing. Square function, or was it? What is this called? Y equals x square. What's this? What sort of
Parabolic
function is?
function, no, convex function.
It's a parabolic.
Convex function.
Finally, quadratic. It's a quadratic function. And what are the properties of a quadratic function? So if I plot x and y, and I plot y equals x square, right? What do I see? I see something like that. Yes. Yeah, sorry about that. It should be at 0. But anyways, you get my point. Now, the crux of this thing is quadratic functions have a minimum, or at least guarantee a local minimum, if not a global minimum. Okay, we'll talk about local versus global a little bit later, but the idea is that these functions have a minimum. That means that there is a point at which the function has a lowest energy or a lowest value, right? And you can find that, right? And that's the geometric interpretation of this loss function. And for simplicity, as people said, okay, there is the errors are going to always be positive and all that, but that is a consequence of the fact that the error function looks like this, right? That is, at some point it will come to 0. So if you let a ball
means,
roll,
like, sir, expectation is like that at some point it will be actual prediction. It will do actual prediction, right?
exactly, at some point you will have a loss where there is minimum there is a minimal loss in the in your predicted output versus the model prediction.
It's like
Sorry,
we are implementing.
I can have my loss function based on the objective of my problem, right?
also that's also fine, but I'm just giving you one instance where this sort of a function can be contextualized as a loss function, because it has a minimum. So that means that if you start somewhere on this function, there is a possibility to reduce the loss to a certain level, right? So that you can make the performance of the model better and better, right? If the landscape is just flat, right, with no bumps, then there is no possibility of doing that, correct? Right? And only if there is a change in the landscape, so that your loss function reduces with time or with change in the parameters, or in this case x, then you have a function that can minimize loss. So that's the point, but it depends on the problem. That's correct as well, because I'll show you another type of loss function in the next slide. But are people do people get this idea that for these sorts of functions, there is a minimum, right? In fact, in certain cases, it guarantees a global minimum, right? But at least it has a local minimum, because if there's an n-dimensional space, if X is n-dimensional, then you don't have a guarantee that there's going to be a global minimum, but at least there's going to be a local minimum. Right? There'll be bumps where you can actually reduce the loss. It depends upon where you start. Okay. Because in this case, if you start somewhere here, then you can drain into this. But if the landscape is very complex, right? Something like that. And let's say if this is the global minimum of the function, if you start here, then you will end up here. But if you start here, then you can end up here. Okay. So there are some nuances here, but the point is that this sort of a loss is quadratic in nature. So it at least guarantees that you will be able to reach a local minimum. Okay.
So since it is a quadratic,
Mhm.
so most of 100% of the time, local minima or the local maxima is a global minima or the global maxima.
Sorry, come again.
So in the quadratic, local minima or global minima, they are like inseparable. They are same.
Local and global is same, you mean?
Yeah, in quadratic.
In quadratic, yeah. Yeah, but in n-dimensional spaces, the landscape becomes a bit complex.
Okay, we are
Yeah.
talking about in
Yeah. For in the 2D case, it's very simple to visualize, right? Let's say you have another dimension here, and then you increase it, then the problem does not become as simple as you know that there is a minimum, right? There is a global minimum somewhere, but you can't guarantee convergence. That's the problem, because it depends on where you start in the network. But the point what I want to make is, you have a loss function now which can be minimized using this, and how you minimize it, we will have a look at it in the coming slides. But this form of loss can actually tell you or actually scale with how well the model predicts your target, right? So if the target is close to the model prediction, then the loss becomes minimum, and if it's very far away, then the loss is high, right? So there is a way in which you can compute this loss function as a function of the output and your targets. So that's one thing. Okay. There is another type of loss function. Anybody have an idea? What is another type of loss function that you can use?
Mean
Mod of y minus y hat.
Come again?
Mean absolute error.
That's fine. That's very, in some sense, similar, slightly in the same
Huber
way.
loss.
Huber loss. So what is that? Can you mathematically express it? What is it? How is it expressed?
So actually, it combines the best of mean square error and mean absolute error.
Okay. Yeah, both of them. I guess there are many variations, but the standard ones that are that's also used. Have people heard of cross entropy loss?
Yes.
Yeah.
Yes, sir.
Okay,
Yeah,
so let's talk about that, but let's talk first about entropy, right? Before we go into cross entropy. So what's entropy?
minus of y log y.
No. What is the intuition? I know the
So
formula.
it defines the degree of randomness within the data.
Sorry, I can hear a lot of noise. So let's
Yeah.
say something is very ordered, right? Yeah. So you have some ordered system which has some sort of physical property, right? And then you have probably a disordered system, right? Something like that. Now, in which case is entropy high? Yeah.
Second case.
Right. So in physical systems, this is how entropy is defined, right? But Shannon, right? Claude Shannon was this guy who came up with a lot of interesting ideas in information theory, right? And he proposed a type of entropy formulation, which we just now was answered, right? If the probability of an event occurring is here, and if I plot entropy here, Anybody know what sort of relationship this will have? So let's say if this is
entropy
0,
Negative log.
right? What sort of a relationship does this have?
So negative logs 1 by p.
Any sort of, what sort of shape the curve has?
hyperparabola, rectangular
Yeah,
hyperparabola.
something like that, right? Yeah.
So what is
So
px here?
Px is the probability of an event occurring, of an event x occurring. Okay, right? And this is say 0.5. Right? Now, what this tells you is, people often understand the formula, but understanding the intuition is much more important, right? That is, when an event is extremely certain, that is the probability of it occurring is either 0 or as 1, then the entropy is low because you are highly able to predict what is going to happen, correct? But if the events are highly uncertain, right, then you cannot make any, or it's at least at chance level, say at 0.5, then you can't make any predictions about which events are going to occur, so the entropy is high. So this is the information theoretic intuition behind entropy. Okay, and as people mentioned, entropy or Shannon's entropy, right, is negative sum over all the events x, p of x into log of p of x, right? Right. So what does this tell you? This tells you that whenever you have to take the event and you have to take the log of the probability of the event and log of probability of the event, multiply them and do it over all possible events x, and then you will get the entropy of the system, right? So this is entropy. In that same sense, what will be the expression for cross entropy?
We have to multiply px py.
So that means if I say of two events x comma y, let me put it as x. So that's nothing but p of x times log of p of y, right? So you're computing the cross entropy. That is, you're taking two probability distributions and you are trying to find the entropy of the system for across these two probability distributions. Okay, very simplistically put, in the deep learning literature, this p of x typically corresponds to what the target is, right? So basically, if you have an image of a cat, right? Let's say you have an image of a cat. So you can basically define, right? You can know that the probability that this is a cat is 1. Right? You can say that. And the model predicts something, right? Let's say the model prediction is something around 0.1. Right? Now, you can use this cross entropy as a way to define loss. This is how you do it. Yeah, same thing. So it is nothing but the same thing, but just written for the binary case, right? Y into log of y hat minus 1 plus 1 minus y into log of 1 minus y hat. That means that if, let's take this case, if the py is lower, right, or pi is, let's say the model is close to 1 first. Let's take that case. Model is close to 1. Then log of 1 is
0.
So this entire loss will tend towards 0, right? But if the model prediction is low, 0.1, then this value will become higher, so the loss increases, right? So this is a way to then look at probabilistic data, right? In fact, what you can do is take the outputs of the network and pass it through. Has anybody heard of this function, softmax?
Yes.
Yeah. Any idea what a softmax function does?
It scales the output with respect to exponential power
and converts them into some sort of a probability measure, right? So takes the output and scales it into probabilities, right? So it tells you then, so if this is the image of if this is output for image of a cat or a dog, for instance, then you can scale that and say that, oh, for this image, there's a 0.1 chance that it's a cat and 0.9 chance it's a dog, for instance. Right? So that can take the respective values and scale it. There are certain parameters. I'm not going into the mechanics of it, but the intuition is that if this is what the model predicts and you compare it with what the actual thing is, let's say, then the loss either becomes higher or lower depending upon the model performance. And now you have another way to compute whether the network is able to match what the target is or how far away the network is from the target. Right? So,
sir, if it is a classification, then we will use softmax.
Right. So if you want to do more classification sort of problems, you would go for softmax. But if you want to do prediction, that is, you want to predict the next value that's coming up, say for example, you can do that for a simple time series and so on, then you will keep it more numerical and you will use the mean squared error.
Okay, mean squared.
Okay. Yeah.
Sir, one small doubt.
Mm-hmm.
So there is a concept of log loss. So it basically penalizes for predicting lower probability, if I'm not wrong.
Yes. Yes.
So how the entropy is different from the negative of so the log loss from the log loss?
I believe the entropy sort of scales also with your, if I'm not wrong. So the log loss is defined as just the negative log of your probability, right? Yeah. So I believe that that's not scaled by your targets, or I'm not sure. I forgot the formulation of the log loss, but I believe that the entropies is another version of the same thing. I don't think they are extremely different, but I think for the log loss there, as you say, that for very small probability levels, there is a penalization in the log loss case compared to this, whereas in this case, I think the system still has a little bit of the loss there. I'll have to check that, but I have to recollect the formulation of the log loss.
Okay.
But I'll get back to you on that.
So if I'm not wrong, so this function, the like now that it's in the first, it also penalize high probability. And log loss just penalize low probability, and it does the like in front of it penalize both higher and lower.
Higher and lower, yeah, exactly. Yeah. So I think at the end of the day, it depends upon the type of problem that you want to solve, right? Like for instance, if you want to make sure that the categories are really, really distinct or separated apart, then you want to use a loss function that will penalize, say for example, low probabilities, because you want them to separate out really well. And if for instance you still want to maintain some uncertainty, because you have to see whether those two information might have some overlap, then you want to penalize really high ones, so it does not predict black and white that one is this compared to the other. So there is still some chance that it could be another image, for instance, right? So there is sort of it depends upon the problem at the end, what you are trying to solve. So that determines that. Okay. And yeah, so if everyone sort of understood this concept, let's look at the idea of a cost function. Okay, what's the difference between a loss function and a cost function?
Loss function will be for individual point, and the cost will be total
for the entire thing. So the idea of a cost or an objective function is basically the average of all losses, right? So you do something like this, is depending upon the number of patterns that you have or the number of inputs that you have, right? You calculate the average of all losses. Any idea why do we do this? Sorry. Why do we do this? Why do we?
This is like adding the context into the log function. So sometimes we want the losses to be high. but sometimes we want them to be there. So we can manipulate losses to get the cost function and contextualize this.
Right, but what is the ultimate aim of that? Why do you do this?
To judge the model is predicting as per our desire.
Correct,
To
but there's
gauge to gauge whether like the entire system is like working. Like loss basically is for like each output node, I guess. But
exactly.
cost will basically tell us the how good is the entire like network, not just
Right.
individual.
That's absolutely correct. But what does that give you? Why do you need to do that? Why can't I optimize the network for individual losses? Okay, I'll answer this in 1 second, where I want to just hone in this point, because the aim of the deep learning or deep learning algorithms will tell you what is the point behind taking the cost function to optimize, right? So the idea is to minimize this cost function. You are not trying to minimize individual losses. You are trying to minimize this cost function. That is, you are trying to find out parameters in the network, right? Be it the weights, and in fact, if there are biases as well. This network has not represented that, but it's implicit, right? That you want to find out those weights that will minimize the cost function J. So now tell me why would you want to train over the cost, or why would you want to optimize the parameters over the cost function and not the individual losses? Anybody?
So I can answer based on like ML experience that we have. So earlier we used to calculate the losses, and if we have multiple features, so with the help of cost function, matrix, we can determine that which features to get more priorities in terms of minimizing the losses.
There's a one word for this. It's people have heard of this, right? Overfitting. Yeah. So the idea of using a cost is it prevents overfitting, right? That means that you are not changing the network to small changes that are occurring with respect to the losses. You are sort of taking the ensemble effect of the loss and then training the network based on that, right? So at the end of the day, you do not want to want the network to learn the data completely. You want the network to be able to generalize to situations. You want it to learn the concept of a cat rather than learn what are the features of the cat that was presented to the network. Okay. Was there a question? Please speak up if you have raised your hand. You can unmute and let me know. Anyways, is that idea clear, right? But often there's a slightly, the downside of training over a cost also. Okay, that costs can, training with over the cost can help you prevent overfitting and help the model generalize. But any downside to that?
Underfitting.
Underfitting, or in sense low sensitivity, right? Sensitivity becomes lower. Like if, for instance, the entire losses sum up, and at the end of the day, it's not enough to drive the network towards the minimum, then you are stuck with a network that's still untrained, right? So it's sort of a balance between you want to fit the network to the problem, but you don't want to overfit it. So it's like a delicate balance between those two things. And that's why we want to typically minimize over the cost.
Sir, how to define that particular boundary?
Yeah. So that depends mostly upon the problem as well that you are trying to solve. So for instance, certain problems you can actually look at the decision boundaries if they are low dimensional, correct? Because you can plot them and actually have a look at how are the classes distributed, what sort of boundaries do they have. But in very high dimensional problems, when you can't do so, You have to rely on the fact that you know how well the model is generalizing to new data, right? So you train the train the model on an initially given data set, and then you see its performance on data that it has not seen, and you see its performance, and you sort of use that as a metric to define this balance, right? Like, do you want to train the network more? Do you want to give it more data? What do you want to give it the same data further? All that, right? So that kind of settles the balance between, okay, are you able to generalize to new information, or are you just fitting to the features of the existing data, right? So because you will see that there's a performance on the training data and the test data, right? So you'll be able to use that information to determine, right? Because when the input is too high dimensional, you can't use visualizations to actually see how the boundaries have fit, right? That's a problem.
Sir, in terms of loss function, so that is basically to define a loss at a given data point, correct? And that's where the stochastic plays in role, right?
Yes, we'll talk about the gradient descent ideas and stochastic gradient descent.
So I'm trying to understand. The cost function is overall, we take the average of the sum of the losses at each data point.
Yes.
And then we generalize on the gradient generic one.
Exactly. Yeah.
And loss is at a given data point, right?
At a given data point. So this is one data point, right? This x1, for example, this say 3 dimensions, one data point in this say 3-dimensional space, right? For this, we are trying to map it to this output, which is 2-dimensional in this case, right? Say, is it going to be a cat or a dog, for instance? Let's say, right? Something like that. Now, what are we doing here is each of these individual points that we take are spread in this 2D system as well, right? And we know where our the dog versus cat lies, right? So you want to sort of push this. So on an average, you are looking at how far a given point is away from it being the prediction of a cat or a dog, and then you're doing it for all the points, not just one single point, right? One single data.
So basically, we are trying to improve the model at each data point.
Yes, we are trying to improve the model at each data point rather than only focusing on one data point, changing it, and then focusing on another data point and changing it. So we're sort of shifting this entire cloud of data points in some way. You can think about it that way.
So sequentially, it will be updated for each data point, correct?
No, it won't be. That's what my point is. That will lead to overfitting. It will do it everything at once, because when you actually compute the cost, right? Because you are minimizing over the cost function, right? That is where we are minimizing the gradients. Then the gradients of the errors that follow will be a sum of all the errors that you get from these individual data points. That is what will be back propagated to the network. I'll give you an example. Okay, there are two ways of doing this too. It depends upon the problem. You can do it sequentially, one by one. For certain problems which are very simple, the sequential method will work. But there are certain problems where where you want good generalization, you want to make sure you do it over the cost.
No, I think I did not convey my problem properly. My point is, suppose we are taking one data point, right? And we give a prediction for that. Now there is a loss, right? With respect to, now once the loss is calculated, I will update my parameters, back propagation.
You don't have to do that. You can even store the errors, right? And then give the next input, store the error, give the next input, store the error, and do what is called, you must have heard this, a batch update. Okay, so you update the parameters of the network in one go for all these errors that you have called. Okay, or you can do it sequentially as well, as you're saying. You compute the loss for one data point, and then you update the parameters. You compute, then you run the network again, compute the loss for the other data point, update the parameters, and so on. So this is what's called a sequential update, right? When you do it one data point after another, right?
But loss will be for sequence or the batch?
So for each data point you have a loss, right?
Hmm.
But if you take all the losses and update it at one go, that's what's called a batch update.
And
Okay?
cost will be the sum of the each error
Sum of the each error that you are getting for every data point. Exactly.
Oh, okay.
Okay.
So, sir, in this example, for example, if I'm giving a image of a cat and it predicts like we got as a 0.1. So means like model predicted it wrong. So that's a loss for a particular image, and it refers to a particular single data point, right?
Yes, exactly. Correct.
So treating in multiple ways. For example, I am going to train my model on a 500 image. So those 500, I have those 500 data sets, and whatever the loss I will getting in each image, that I can either go for the sequential or either I can go for the batch update.
Batch update. Yes, perfect. That's the logic. Yes. Or you can you don't have to do it in 500. You can do it in like 50 images, right? You present 50 and then you do a batch update. You then present another 50, do a batch update, and so on and so forth. So that way what will happen is you would not train the network to these small local changes, right? There could be a possibility that in one case, right, the network predicted that it was it was an image of a dog, right? And the network predicted low probability for a dog, right? And you updated it very much. And then the next time you presented it for a cat and the network predicted it very wrong for a cat, and then you updated. Next time you present a dog, then it might oscillate, right? It might not converge to the proper value. So there might be oscillations in the weights or the parameters, right? Whereas if you collect all the losses, right, which because later in the stage, right, you could see that there are errors that are being computed which will update these weights in a much more smoother fashion, right? And that's where the batch update helps, right? It does not fluctuate the parameters for these individual losses, but takes the entire loss as a whole.
So, sir, are we saying that if we do a sequential update, like if we update the loss, then we will use the loss function, but if we are doing batch update, then we'll use the cost function.
Exactly. Most of the times you use the cost function. I'll actually even, in fact, now I'm going to show you an example where I do use the loss function at every single point and then try and do an update, because it's a very simple problem. But for very complicated problems, you would go for the batch update, where you will try to minimize over the cost function, right?
So batch is actually intermediate between the loss and cost.
Right? Yeah.
Okay.
You want to basically take all the losses that are there for a set of images and then update it in one go. That's what's a batch update. Okay.
So batch update isn't cost, right?
So batch update isn't cost in the sense it does take into account the cost, right? Because it takes into account these individual losses, right?
Okay.
It does. So look at what the formulation for the cost is. Right? So it's a sum over all these losses. So at a given instant, right? Yes, your average of all the losses. Okay, are you guys confused with the fact that losses are seen at every time step? See, the loss is basically this, right? Where is it? So let's take the mean squared loss, right? This can be for every pattern that you see, right? If this is sort of an n-dimensional vector, it will be some yi minus or yp, say for let's say given pattern for what it was predicted. So this is going to be your loss, right, for that one pattern that you got. Okay. and your cost is sum over all those losses, right? That you see.
Yeah, means like all the losses which.
So yeah, I think
to divergence, right?
Sorry, come again.
Means like if I sum all the losses, means that is the cost which I have to pay.
Correct.
We have not reached that.
Reach the so okay, this is the thing, right? Okay, let's do this. So let's compute the loss for this particular output. Let's say you give an image of a cat here, right? And it is a let's say it is a dog, for instance, or it is predicting as a dog. This is for the, so let's say this node is corresponding to that. It's saying, okay, this is 0.9 and this is say 0.1 or something like that. Let's say that's the prediction, right? Now, how will you compute the loss for this? What sort of loss will you compute? And you know that your predicted
both
is 0,
right?
Yeah.
Cost, we have to add both losses, right?
Yeah, you have to add both losses. So what will you do? You will do cross entropy loss here. Simple. Yes. So you will find out what is the probability that it is a, what did I say? This was dog, this was cat, right? So this is 0, this is 1. Let's say. Right? So it's predicting it's a dog, the network. So the loss will be high, right? And then the sum over all these individual nodes will be your cost, because that tells you whether how far the network is away from what you are actually predicting. So in this case, it's supposed to do 0, 1, but it's doing something like 0.9, 0.1. Okay. So that's going to be your cost. And what you are going to do is you are going to take that information and you're going to try and minimize that information. And you can do this in two ways. One is to do it sequentially, right? So for every loss that you calculate, you update the information, right? Or you collect all the losses and do it as a batch update. Okay.
Sorry, sir. Last line. Collect all the losses
and update it in a batch. I'll tell you how the batch update works.
But
yeah.
All the losses is cost, right?
Oh, you mean to say, okay. Oh, shoot. Yes. So at every point you have a cost. Sorry. Yes. Oh, that was the confusion. Yes. So at every input you have for a given input you have a cost, right? Because which is the sum of all the losses. Let's do it this way.
Yes.
You are defining losses at each layer.
No, not each layer. At the output only, right? At each node.
Yes. Correct.
At each node will have a loss, right? Because
yes.
you will find that this is different from your predicted output in some way, right? And the cost will be the sum over all the losses.
L1 plus L2.
Yeah. And
so,
then,
sir,
yes.
just so assuming that we were classifying the digits, right, 0 to 9. So, and we gave a image that is corresponding to, let's
0.
say we gave an image of an 8. Okay. So, like there will be 9 output nodes, I'm guessing, like, sorry, 10 output nodes, 0 to 9. So each will have a loss. But
yes.
And then the cost will be like the summation of
all the losses. Yes, because it might initially predict that zeroth node might be high, second node might be low, and so on and so forth. The sum of all that will give you a representation of the cost, right? And which is what you are trying to minimize. Because if you minimize that, at the end of the day, you will find that the node that corresponds to the number 8 will be high and the rest will be low, right? That's what you want. That's what will minimize the cost at the end of the day. Yes. So in that sense, right, this is basically the I to n is basically your node, right?
Yeah. Output node, right, sir?
Output nodes, yeah. Yeah, sorry about that. Yeah. So that was confusion there, huh?
It is all the nodes, right? I mean.
Yes, all the nodes in the output. Yes.
So
Exactly.
I was thinking about the data point in machine learning for each data point.
For
So
each data point, you get a cost, right? Because individual losses sum up to give you a cost. So that was the difference, right? So that can be done sequentially or via batch update too. That's a separate point from that. The point is that every data point that you present will have a cost that's associated with it, which is the sum of all these individual losses.
So means like batch update belongs to how we are going to add the losses, right? To create a cost.
To create the cost, exactly. Because at individual level, you will get losses for a given pattern. And if you combine all the losses across, say, a set of inputs that you give, you get a cost, right? And that cost function will be a little bit more smoother than the individual data point itself, because then you will have it to be a little bit more noisy, right? Because that might lead to a little bit overfitting compared to if you take the information across a lot of input data points and then you add those costs together.
Loss and cost are basically loss and cost are two different entities only in deep learning. There is no significance of loss and cost individually in machine learning data, right?
I don't think so. In deep learning, it makes a lot of sense because you have these parameters that you have to train, right? And the training of these parameters is highly dependent on what's the time, guys?
Already 12.
12, right? Yeah. Okay, so we'll stop in a couple of minutes, but I want to hone this point before we leave this class, because I want to make sure that this point is clear. Yes, so in deep learning, you want to train these this model, these networks, and these weights, and you want to make sure that the training of these weights are happening in a way that does not oscillate these parameters. That is, it does not change rapidly, right? And in order to do that, you want to make sure that the cost is something that changes smoothly across time, and so that you want to average across all the losses and or these individual losses that you get, and that might produce a smoother change in the gradient. In fact, I wanted to cover backpropagation today, but it looks like we don't have the time. We'll look at it tomorrow, but hopefully this is clear.
Yes.
Yeah, so that's basically one of the motivations. It prevents overfitting. That's why you don't want to do it over individual losses. And I'll end it with here, because next class we'll look at one example before. So if you give me like 5 minutes, we can complete this. So idea of gradient descent, this is basically the fundamental algorithm in deep learning, right? This is it. This is what you use most of the times. You often use a version of this called stochastic gradient descent. People must have heard of this, or even done some version of this in machine learning, right? So what is the idea behind gradient descent? Okay. The thought is very simple. You have like an objective function or a cost function which has some landscape. You first start by guessing a solution. That means you say that, okay, I'm somewhere on this landscape. Let's say that the landscape looks like this. Okay. This is my parameter space. And this is my objective. Okay. And I say I'm somewhere on this space, right? This is my solution. I guess this is my solution. Okay. This is the set of parameters I start off with. Okay. Now what I'm doing is I'm computing the error. I'm saying that, okay, if this is my parameter space and I input information through the network, what happens to the objective function? What is my error, right? Okay. Now is that possible to use the error to update the parameters in some way that I can minimize this objective function? Now, but just by looking at this plot, what can you say? What is the way in which you would like to do it? And what is the idea behind gradient descent?
We'll slowly move forward step by step to reach the minimum.
No, but what informs that step?
So like we have to update our parameters so that we can reduce the error.
Correct. But what informs that?
Error.
Because
that gradient at that point.
The gradient. Error. The gradient. Oh. The error, but the error direction or the function's gradient, the function's slope informs where to go. Okay. When we say the function slope, if I'm here, right, if I compute the gradient, we are trying to push this in a direction. In fact, I would like to be here. Let's say this is our starting position. Forget about that, because this way the error is, the gradient is going the other direction. But let's say I'm here, right? I compute the gradient. That means the slope at this point. Let's say. And then I'm asking the question, I want to go in the direction of the slope where the slope is sliding downwards. Okay. I want to take that direction, which is in this case, this direction, right? So you're taking the direction which takes you down this gradient. Okay. In a hope that you might end up in a place where you see this bowl or the minimum. Okay. And that is why this algorithm is very sensitive to initial conditions, because if the landscape has many of such potholes, you have to be very careful about where you start from, or you need to know. Only then can you drain into the global minimum, but that's not guaranteed. But point is this, right? You guess a solution, you compute the error, you update the parameters, you guess the solution. That's the algorithm. But the direction in which you move depends upon the gradient. Okay, so this is a simple cost function that you have.
Sir, how we will understand we are at minimum cost now?
So once you are at this location, right, the gradient is flat, right? Okay. If you are slightly here, you will move here. If you're slightly here, you'll move here. At this point,
zero at that point.
Gradient will become 0 at this point, right? So there is no more way to update, right? The gradient becomes 0. So wherever there is a gradient, then you use the negative of the gradient, or you travel in the direction that slides you down the gradient. Okay. And once you reach this minimum, the gradient becomes 0. So there is no more update. Yeah, got that?
So
was there a question?
Like taking the double derivative.
Sorry?
To find it out at where in the minimum. So we take, instead of gradient, we also take double derivative.
So the double derivative just tells you whether it's a minimum or a maximum, right? It does not tell you how to reach there. The gradient tells you the current slope or the current slant that you have, right? So if you are here, right, this is the slope at this point. Oops. Let me erase that. That's the slope, right? And you want to take the direction that takes you to the negative of the slope or down this gradient. And that's how you will end up in that bowl. Okay. If this corresponds to the minimum error, for instance.
Sir, is there any other algorithm, like you said, it's sensitive to the point where we are starting? So are there any other algorithm?
Yeah, there's something called stochastic gradient descent, which is a slight modification to this. So in that case, what happens? Let's take an example, right? Now, if you are here, right, and then let's say you go down the gradient, you end up in this small local minima. Okay. Now, imagine if you just followed the gradient, you will be stuck here, right? But this is not the optimal solution, because a further lower minimum exists here, right? That would take you that will minimize the objective function even better and sort of give you a better performance, let's say. Stochastic gradient descent, what it does is, instead of just going down the gradient, you are also adding some random noise to this. In fact, what you're doing is you're perturbing this, right? And there could be a random push in some way that takes it here, and when it reaches this peak, now this is a sharper gradient, and then it flows down into this, right? So what happens in those cases is you are giving some momentum to the parameter space, right? And you're pushing it in random directions. So if it is if it's not a very deep wedge, if it is a small shallow minimum, it's a possibility that you will come out of the minimum if you give it enough noise, right? But the same thing, you might ask, what happens here at this current location? If the same thing happens here, then the bowl is big enough that it might not allow the point to go out of this, right? So even with the noise, it might just get stuck there and return there, right? But in other places, there is a chance that it might just get pushed out, and you might find this better minimum solution, right? So the idea of stochastic gradient descent is that you use noise as a way to perturb the system so that there is a chance of finding a better minimum, right? And in fact, this is one algorithm that's used often in deep learning to find out optimal solutions for the weights.
But so still we could encounter a problem where there are two bows which are big enough, but one is bigger.
Of course. At the end of the day, right, if that minimum could also be a good solution to the problem, right? In fact, you should think of it like this. Is achieving a global minimum the objective of deep learning? I don't think so, right? The objective of deep learning is to actually find a solution that works and generalizes your problem. If that is happening with a certain solution space, right, why do you care then, right? In order to go to that other space, which might be either as good or maybe a little bit better, right? Now it does your problem or solves your issue, right? I'm saying that if this is the case, right, let's say this is the scenario. This is your objective function space. This is your parameters. Being here or here does not make too much of a difference, right? Yeah, both are probably good solutions for the problem. Yes?
Yes, sir.
Okay, guys. So we'll end here. Tomorrow we'll complete with the introduction, right? I'll show you one example of a perceptron. A simple perceptron and how that works, how we can apply these ideas of gradient descent and apply it on a very simple problem. And then we'll look at some of the types of neural networks and their applications, deep neural networks and their applications. And from next week, we'll start convolutional neural networks. Okay.
Sir, can you share this?
Sir, last question here.
Yes.
So, what is here meaning by like a stochastic?
The idea of a stochastic or the stochastic part is, in addition to moving towards the negative of the gradient, you also introduce a small noise to the system. That is, you perturb the system in this parameter space. You push it here or here slightly, okay, in a random direction. If it happens so that it is in a shallow sort of a space, there's a possibility that the noise can push it out of this, right? And that's the idea of the stochasticity. And if that noise is able to push it out of that, there's a possibility that it can drain into a better minimum or a much more lower minimum. That's the idea.
So idea is like adding the random some little noise.
Yes. Adding a little noise in addition to moving towards the negative of the gradient. Yeah. So you use that as well as some noise to make sure that the system is able to find out if there is a better solution than what it is right now. And as pointed out, there is a possibility that it might just get stuck. But at the end of the day, it depends on the solution, right? If the solution is able to solve the problem that you are posing it, either to classify images or to perform some form of temporal prediction, or do some simple classification. If that works really well, you don't care whether you are stuck there or not.
So there is also the concept of like, so what I understood was like, because of the batch gradient descent, it's very ineffective. I mean, kind of takes a lot of compute. That is why we use stochastic, so that we individually iterate over each data point.
Correct. But if you imagine that is the ultimate aim, right, of stochastic gradient descent, you want to make sure that the solution that you get does not depend upon certain small individual number of data points. It depends upon the solution to the whole problem, right? And this is a type of algorithm which can take you towards that solution. There are many other variations of this. And in fact, many people have even used what's called stochastic resonance based models, or algorithms which can do, where you use correlated noise instead of just random noise, to kind of make sure that the push is in certain direction more stronger than the others. There's some, I'm not too familiar with that literature, but there are ideas like that. But the main intuition behind stochastic gradient descent is to make sure that there is a possibility that you can, push the state into a better minimum in case it is stuck in some sort of a shallow space like this. That's the intuition basically. How it is being implemented depends upon the type of problem, right? You can implement it in a batch way, also in a sequential way. But the ultimate aim is that. Okay. All right, guys. So let's end it there. Thank you.
Thank you.
Thank you, everybody. All right. So see you tomorrow at 9:45.
Thank you, sir.
See you soon.
Thank you, sir.
Thank you. I'll stop the recording once. Let me